Well, here's a question about projectile motion where the air resistance is proportional to the square of the velocity. The question tells us that its constant of proportionality is 0.4. Now, the resistance is always opposite to the direction of motion. We're going to take gravity as 10, and the original conditions are this, that the original velocity is 10 root 3 meters per second at an angle of 60 degrees to the horizontal. So instead of writing that all in words, this here is the initial situation. I'm going to take my origin, x is 0, y is 0, at time 0. What I want to do is find the 6 equations of the motion. X double dot, the acceleration horizontally, the velocity horizontally, and the displacement horizontally. Y double dot, the acceleration vertically, the velocity vertically, and the displacement vertically. I also want to make a Cartesian equation, so instead of having, like these will all be functions of t, instead of having t as the parameter, I want to eliminate that and make y as some function of x. Then I might be able to graph it on a software program like Desmos and just see how close to a parabola the motion really is, given that there's some resistance that's proportional to the square of the velocity. So let's start. Here's the actual question. Let's start because we want to find the maximum height and horizontal range, and then we want to make a sketch. So let's find these 6 equations. The 6 equations of the motion. So horizontally, this is equal to minus m times your 0.4 v squared. Mass times acceleration in total is equal to minus mass times 0.4 v squared. The resistance is opposite to the direction of the motion. So if I divide by m, I get this here. Now I should put a little x there because we're talking about the vertical velocity. In fact, I can replace this little velocity with a little x with x dot. So I might do that. It's x dot squared. X dot is being squared there. Now, x double dot, that's just the derivative of the velocity with respect to time. Acceleration is the derivative of velocity. Normally, acceleration is written dv dt, right? That's v velocity horizontally there. But I'm going to write down that that's d of x dot dt equals negative 0.4 x dot squared. Because the acceleration is the derivative of the velocity. Now, if I separate out these variables, d of x dot on x dot squared equals minus 0.4 dt, and do my integral that way, well, this is like saying dy on y squared, if you like, and you could always rewrite it somewhere else on the page and then come back. But this is going to be minus, oh, there goes a spider down past me, minus 1 on x dot, because that's the derivative of 1 on x dot squared, the integral of 1 on x dot squared. And this will be negative 0.4 t plus c. Now we said we're going to choose this to be our origin, and we know also that at the start what our horizontal velocity is. It's the horizontal part of this vector here, which is 10 root 3 at an angle of 60 degrees to the horizontal. So going horizontally, it's 10 root 3 times cos 60 is the horizontal component of that original 10 root 3 vector. So I'm saying when t equals 0, the horizontal velocity is equal to 10 root 3 cos 60, which is 5 root 3. So I can pop that in there, minus 1 on 5 root 3 equals 0 plus c. C is minus 1 on 5 root 3. So we get that minus 1 on x dot equals negative 0.4 t and minus 1 on 5 root 3. All right, now I'm going to sort that out to make x dot, the horizontal velocity, the subject. So first of all, minus 1 on x dot equals, actually 1 on x dot equals 2/5 of t plus 1 on 5 root 3. So 1 on x dot equals 2 root 3 t plus 1 on 5 root 3. So flipping both sides, that's 5 root 3 on 2 root 3 t plus 1. And that gives me my equation for my velocity. So I'm going to need, oh no, I can move that along. I've got that for my equation for my velocity. And now I'm going to integrate again with respect to time in order to get the displacement horizontally. So this is dx dt. So dx dt is equal to 5 root 3 on 2 root 3 t plus 1. So now I need to work through to find what x is. So dx on 5 is equal to root 3 on 2 root 3 t plus 1 dt. Now I look at the denominator and I see that it's 2 root 3 t plus 1 and its derivative is 2 root 3. So I want 2 root 3 on the top. If I'm going to do that, maybe I'll multiply both sides by 2, and now I can find that the natural log of the denominator is the integral of this side. So I get 2/5. Oh, if I integrate both sides, I get 2/5 of x equals natural log of 2 root 3 t plus 1 plus c. When t equals 0, x equals 0. So we get 0 equals natural log of 1, which is 0. So therefore c is 0. So I actually get an equation for the displacement horizontally that's 2/5 x equals natural log of 2 root 3 t plus 1. So I get x equals 5 on 2 natural log of 2 root 3 t plus 1. So I'll put that in a box so I can find it. So I'm finding my 6 equations of motion, and I've found so far the acceleration horizontally, the acceleration vertically, the velocity horizontally, and the displacement horizontally. Now I'm going to look at the acceleration. That's the vertical stuff. let's look at the acceleration vertically. So y double dot. Well, that acceleration times the mass is equal to minus mg and minus 0.4 v squared, where v is the vertical velocity, so I'll put a little subscript y there. Now I can actually minus m times that. That's the two forces that are acting against. Yeah, that's the situation there. I can divide by m and get y double dot equals minus g minus 0.4 and instead of v subscript y, I'll just call it y dot like it is being squared. All right, now instead of g, of course, I can put 10. And instead of 0.4, if I want, I can put 4 over 10. The reason I'll do that is I'm going to factorise 4 over 10 out of this. So y double dot equals minus 4 over 10. Well, that'll be plus y dot squared. That'll be 25, because that'd make that minus 110, which is minus 10. Okay, so now this here is d of y dot dt. The derivative of the velocity with respect to time is the acceleration. So that's minus 4/10 of 25 plus y dot squared. So let's separate the variables again. dy dot on 25 plus y dot squared equals minus 4/10 dt. Okay, and we're going to take the integral of both sides here. So the integral of this side, that's 5 squared plus y dot squared. So that's an inverse tan. Inverse tan of, it's a fifth inverse tan of y dot on 5. And this is equal to minus 4 on 10t plus c. So we need to figure out what c is there. Right, so keep that bottom bit there. And when t equals 0, y dot equals, now y dot is the vertical part of the original velocity vector, which was 10 root 3 at an angle of 60 degrees to the horizontal. So we want 10 root 3 sine of 60 degrees. Which is 10 root 3 times root 3 on 2. 10 times 3 is 30 on 2 is 15. That's 15. So when we put 0 in for t, we get 1/5 inverse tan of 15 on 5 equals c. So that means we can write what we had as 1/5 inverse tan of y dot on 5 equals minus 4/10 t plus 1/5 inverse tan of, and 15 on 5 is 3. So there we go. I just want to get y dot by itself now here. So I'm going to use a little trick based on the formula for tan of a minus b. So first I'll get, I'll times everything by 5 to make this look a bit better. This will be inverse tan of y dot on 5 equals minus, that's 2/5, so minus 2t plus inverse tan of 3. And this would really be inverse tan of 3 minus inverse tan of y dot on 5 equals 2t. If I got the 2t by itself over on that right-hand side, and I times everything by -1 to sort out the negatives that were going on. All right, so this trick is going to, I'm going to go to this extra bit of board here and write it out. So I'm going to let A equal inverse tan of 3 and B equal inverse tan of y dot on 5. Just make sure you can see that there. All right, so therefore, tan of A equals 3 and tan of B equals y dot on 5. So I'm going to actually look at what is tan of A minus B. Well, we know the rule is that that's tan of A minus tan of B on 1 plus tan of A times tan of B. All right, that's a rule that you're expected to know. You can derive that, but I don't want to do that at this point. Let's just accept that that's the rule. Then we can say that tan of A minus B is tan of A minus tan of B on 1 plus tan of A times tan of B. And if we sort this out, we'll end up with 15 minus y dot over 5 plus 3y dot. So all I did was times the top and bottom by 5 if that will work. So that's what tan of A minus B is equal to. I'm going to transfer that up to here. Tan of A minus B equals 15 minus y dot on 5 plus 3y dot. So A minus B is equal to inverse tan of 15 minus y dot on 5 plus 3 dot. But what's A minus B? That's tan inverse tan of 3 minus inverse tan of y dot on 5 is equal to this. All right, so we know that from our line before, from our working before, that our inverse tan of 3 minus our inverse tan of y dot on 5 is 2t. So inverse tan of that minus that is this, but that's equal to 2t. That's equal to 2t. So I'm going to write that down up here where I've got some room. The fact that inverse tan of 15 minus y dot on 5 plus 3y dot, this, which equals this, is equal to 2t. Oh, that's no good. Running fast out of pens that work. Okay, inverse tan of that equals 2t, so 15 minus y dot on 5 plus 3y dot is equal to tan of 2t. So now we're able to expand that out and make y dot the subject. You know, we've got 15 minus y dot equals 5 tan of 2t plus 3y dot tan of 2t. So 15 minus 5 tan of 2t equals 3y dot plus, sorry, y dot into 3 tan 2t plus 1. So I just added y dot to both sides, and I added 5 tan, subtracted 5 tan 2t from both sides. So I get that y dot is equal to 15 minus 5 tan 2t on 3 tan 2t plus 1. All right, now the integration to get from here to y is quite long-winded. I tried originally a substitution to let u equal, let tan t equal u over 2. Struggled a bit there. I then tried a substitution of u equals 3 tan 2t plus 1, which there was another substitution after that, and I ended up with the appropriate answer. And the answer that I ended up with for y was 5 on 2, the natural log of cos 2t plus 3 sine 2t. So I've done another video which is just this integration step from here to here, because it takes a solid half an hour of getting through the substitution steps and so on. It's not that ridiculously difficult, but this would just draw this one out beyond ridiculous. So you can go to that video if you want to see what the integration is to get you from here to here. But now I have the 6 equations of the motion. I might go back to my original question and pop them down all together, and then we'll answer what we've been asked to do. So originally, this is what we were given, our picture, and I'm going to write down the 6 equations of motion that we've just found, and then we're going to answer those questions there. So the first one we found was that x double dot is equal to minus 0.4 x dot squared, and x dot was equal to 5 root 3 on 2 root 3 t plus 1, and x was equal to 5 on 2 natural log of 2 root 3 t plus 1. So that was those ones. And then for the y equations, we had y double dot equals minus g minus 0.4 y dot squared. And then we had y dot turns out to be 15 minus 5 tan 2t on 3 tan 2t plus 1. And will we fit the other one in down there? Yeah. And y is 5 on 2 natural log cos of 2t plus 3 sine of 2t. So there's our 5 equations of the motion that we can now use to answer our question. Yeah, you can see them. So the first question is, what's the maximum height? And the maximum height happens when it's got to the top of its flight right? Top of its flight, it stops vertically. It goes up, stops, and comes back down. So when the vertical velocity is 0, that's going to give us the time when we get the maximum height. Once we know that time, we can put it into the vertical displacement and work out what that height is. So our vertical velocity is here. To make that equal 0, that means the numerator is 0. So 15 minus 5, 10, 2t has to equal to 0 for our vertical velocity to be equal to 0, which means 10 of 2t equals 3. So 2t equals inverse 10 of 3. And t equals whatever that is. So let's pop that in the calculator now. Inverse 10 plus that, we get 0.6245 seconds. That's the time where we get the maximum height. So now we need to put that in to get the actual maximum height. We need to pop that into here. So y equals 5 on 2 natural log of cos. Now, because it says cos of 2t, I'm just going to go back where I had 2t, and that's cos of inverse tan of 3 plus 3 sine of inverse tan of 3. Right, so the natural log of that times 5 on 2, and the maximum height turns out to be 2.878 metres. So it gets about 2.8 metres high. All right, now we're interested in the horizontal range. For the horizontal range, the vertical is 0. It's 0 here vertically and 0 here vertically. So we need the vertical displacement to be 0. So I look at my vertical displacement equation and how that is ever going to be 0. Well, the natural log of this is 0. We know the natural log of 1 is 0. So the stuff in these square brackets here must equal to 1. So basically, I need to solve cos 2t plus 3 sine 2t equals 1. So I'll give myself a bit of room to solve that here. So I'm trying to solve cos 2t plus 3 sine 2t equals 1. Use the t formulas, but I'm going to use the auxiliary angle method. So I'm going to appreciate that this is like r cos alpha cos 2t plus r sine alpha sine 2t is equal to this piece here. So that's going to equal 1. All right, so my r cos alpha is equal to 1 and my r sine alpha is equal to 3. All right, now if I divide those two equations, I get tan of alpha equals 3. So alpha equals inverse tan of 3. And if I square both equations and add them, I'll get r squared equals 3 squared plus 1 squared, 10. So I'll get r equals root 10. So we're able to say that root 10 cos of 2t. Now, it's a plus, so it's actually a minus in there. Minus inverse tan of 3, right, is equal to 1. Okay, from there, we can say that cos of 2t minus inverse tan of 3 equals 1 on root 10. So 2t is equal to the inverse cos of 1 on root 10 plus the inverse tan of 3. And then t will be just that divided by 2. So let's see. I need the inverse cos of 1 on root 10 plus the inverse tan of 3, and then divided by 2, I get 1.249. So it's in flight for that long. And then we need to put that into the horizontal equation of displacement, which is this one here, in order to find what the horizontal range is. So I'm going to pop that t equals 1.249 seconds into the, it says x is equal to 5 on 2 natural log of 2 root 3 t plus 1. So 5 on 2 natural log of 2 root 3 times 1.249 plus 1. I put that in the calculator and I get 4.181 ... So about 4.2 meters. So it goes across about 4.2 meters. It goes up about 2.9 meters. Now, the final thing we were asked to do in our set of questions was to do a sketch, like on Desmos or some software program. So what we need to do is just get an equation of y equals some function of x, rather than y equals a function of t and x equals a function of t. So I'm just going to get that equation, but I'll leave it up to you to sketch that on Desmos and have a look at how it compares with a standard equation of a parabola, right? Because it's got a bit of air resistance proportional to the square of the velocity. So it's not going to be a nice parabola. There's going to be some skew happening. So the final thing we want to do is we want to take our two equations, x equals 5 on 2 natural log of 2 root 3 t plus 1, and y is equal to 5 on 2 natural log of cos 2t plus 3 sine 2t. So these pair of equations, and we want to eliminate the parameter t. So what I might do is I might take this one and see what t is as the subject, or even 2t, because I can pop 2t into there. So that's 2x on 5, and that'll be e to the 2x on 5 will be equal to 2 root 3t plus 1. So 2x, I'll do 2x on 5 equals that. So e to the 2x on 5 minus 1 all on root 3 is going to equal 2t if I rearrange that. So you can spend time rearranging that, but that's what I get. So that means y equals 5 on 2 natural log of cos, and instead of 2t, I've got e to the 2x on 5 minus 1 on root 3 plus 3 sine and e to the 2x on 5 minus 1 on root 3. So natural log of that times 5 on 2, and that's going to be my equation that's Cartesian. And if you put that into Desmos and plot it, you'll get the picture of our projectile, which is working under air resistance, which is proportional to the square of the velocity.